This is Module 37 of Mechanics of Materials Part 1. Today's learning outcome is to calculate the principal strains, the maximum in-plane shear strain, and the orientation of the principal planes based on the strain gauge Rosette measurements that we had. And so here's where we left off last time. We had these three in-plane strains, normal strains that were measured. We went ahead and found the in-plane strains, both normal strains and shear strain. Now, today, we're going to go ahead and use Moore's circle to find the principal strains, max in-plane shear strain, and the orientation of the principal planes. So here is our in-plane strains, and what I'd like you to do now is to draw a small element and show the strains on that element, and come on back. Okay, here is the element with the strain shown on it. And now we're going to draw Moore's circle for strain. Let's start with the vertical face where I have 600 in tension strain, normal strain, so that's positive. And then I have a counterclockwise shear strain of 150, but I plot gamma over 2, so that's going to be minus 75. So I go out 600 and then down 75 for my horizontal face. And for my vertical face, I've got 350 positive because it's in tension. The shear strain is going to cause counterclockwise rotation, so it's positive by my shear convention. I use half of 150 again, so I'm going to go 350 and then up 75, and that's my vertical face. So 350 and 75. And I leave the mu's off again for shorthand. I can draw a line in between these two for my diameter, and then I can draw my Moore's circle. Okay, first thing I want to do is find the center. That's going to be the average strain. So we've got 600 plus 375 divided by 2 for our average normal strain, which ends up being 475. So this is 475 and 0. Let's now do the radius. So I've got the radius is equal to, let's take this triangle here. I've got 600 minus 475 squared plus 75 squared. And the square root of that will give me my radius, and the radius ends up equaling, if you calculate that out, 145.8. And so now I can draw a line up from the center to the very peak of the circle. That's going to be my point. Well, that'll be 475 for the normal strain, and then 145.8, which means that the gamma max over 2 is 145.8, or my max in-plane shear strain is going to equal twice that, or 292 mu radians. I still want to find my principal strains. If I add the radius to 475, that's going to give me my first principal strain. So epsilon sub 1 is going to be 475 plus 145.8. And then rounded to 3 significant figures, that gives me 621 mu millimeters per millimeter. And my other principal strain, epsilon 2, is going to be 475 minus the radius of 145.8. And so that's going to equal 329 mu millimeters per millimeter. That's our other principal strain. Okay, and so that's a good good Moore's circle for strain. Here I've gone ahead and plotted it out so that it's much cleaner and easier to see. The last thing I want to do is find the orientation of the principal planes from the XY axis. So let's take from the horizontal face this angle 2 theta sub p on Moore's circle. And so sine of 2 theta sub p is going to be equal to the opposite side, which is 75 over the hypotenuse, which is the radius, which is 145.8. And so if you calculate that out, that gives you 2 theta sub p equals 30.96 degrees. That's twice the angle on the small element, or the small block, and so theta sub p is equal to 15.5 degrees, and we're rotating counterclockwise from the horizontal face. So I can now draw a properly oriented stress block, or stress or strain block. So we can now draw a properly oriented block. And so I have my horizontal face, and I'm going to rotate 15.5 degrees from the horizontal. So this is 15.5 degrees. And on that face, we're going to have epsilon sub 1. Our principal normal strain is 621 millimeters per millimeter. It's positive, so it's going to be in tension. So this is 621 millimeters per millimeters. I turn 180 degrees on Mohr circle, which is 90 degrees on my block, and I get positive 329 millimeters per millimeter. And we're going to have equal on the other sides. And so that's a good oriented stress block, and we've solved the problem. And so you should have a good handle now on finding strains experimentally, converting them to the in-plane strains for 2 dimensions, and then using that data to find your your in-plane principal strains and maximum shear strain, in-plane shear strain, and the orientation for that. And so we'll pick up again next time.